This video will provide an overview of the key concepts covered in Chapter 17, Quality Control and SPC. Recall from Chapter 6 where we introduced a number of simple control mechanisms such as checklists and standard operating procedures to help manage quality. These are relatively cost-effective means of managing quality, however, they generally represent a reactive approach to quality control, since contacting customers after a poor service experience only uncovers the damage that's already occurred. This requires extraordinary measures for service recovery and often results in lost customers. The task of quality control, therefore, is to ensure that a good or service conforms to specifications and meets customer requirements by monitoring and measuring processes and making any necessary adjustments to maintain a specified level of performance, and represents a proactive approach to quality control. Any control system has three components: 1, a performance standard or goal; 2, a means of measuring actual performance; and 3, a comparison of actual performance with the standard to form the basis for corrective action. Good quality control systems work to build quality in at the source, where people responsible for the work control the quality of their processes by identifying and correcting any defects or errors when they are first recognized to occur. This requires that employees have good data collection, observation, and analysis skills, as well as the proper training, tools, and supportive management. Quality control systems consist of quality control practices in both manufacturing and in services. In manufacturing, quality control is generally applied at 3 points in the supply chain: at the receiving stage from customers, during various stages in the production process, and at the finished goods stage. Therefore, manufacturing requires firm engagement in supplier certification and management to eliminate or reduce poor quality materials coming into the process. In-process control involves ensuring any defective output does not leave the process. And finished goods control is often focused on verifying that the product meets customer requirements, perhaps by functional testing, such as plugging in a television before it's packaged. As we would expect, not all products or services are perfect. They're all subject to different kinds of variation, which can occur for many reasons, such as inconsistencies in material inputs, changes in environmental conditions like temperature, humidity, machine maintenance cycles, customer participation and self-service, tool wear, and even human fatigue. Some variation is obvious, such as inconsistencies in meal delivery times or food quantity at a restaurant. Other variations, such as minute differences in physical dimensions of machine parts, are barely perceptible. Common cause variation is the result of complex interactions of variations in materials, tools, machines, information, workers, and the environment. This type of variation is a normal and expected part of the process and can't really be controlled. Special or assignable cause variation, on the other hand, arises from external sources that are not inherent in the process. They appear sporadically and disrupt the random pattern of common causes. This kind of variation can occur because of tool breakage or even human error. Keeping special cause variation from occurring is the essence of quality control. If no special causes affect the output of a process, we say that the process is in control. When special causes are present, the process is said to be out of control. A process that's in control does not need any changes or adjustments, whereas an out-of-control process needs correction. Statistical process control, or SPC, is a methodology for monitoring the quality of manufacturing and service delivery processes to help identify and eliminate unwanted causes of variation. Many customers require suppliers to provide evidence of statistical process control. SPC relies on control charts. A control chart is a special type of run chart to which two horizontal lines called control limits are added: the upper control limit, or UCL, and the lower control limit, or LCL, which are statistically calculated. Here's an example of a control chart. Here's the center line, and these are the upper and lower control limits. All of these data points fall randomly within the control limits and represent normal cause variation. We can say this process is in control. Constructing control charts generally includes 6 steps. Step 1 involves preparation, where we choose the metrics to be monitored and controlled, such as temperature, speed, or diameter. We then determine the sample size, that's the number of observations in the sample, and the frequency, or how often sampling is to take place. For example, if we want to measure the temperature of lattes at Starbucks, we might randomly test the temperature of 5 lattes every hour, and then we set up a control chart. Step 2 involves data collection, and includes the recording of data, calculating relevant statistics such as averages, ranges, and proportions, and plotting the stats on the chart. Step 3 involves the determination of trial control limits and the center line for the control chart. Step 4 involves analyzing and interpreting the data to see what story it tells. Here we look for assignable cause variation, investigate out-of-control conditions, and eliminate data if necessary and recompute the control limits. Step 5 involves using SPC as a problem-solving tool by continuously collecting and plotting data, identifying out-of-control conditions, and taking corrective action. Finally, Step 6 involves determination of process capability using control chart data. Many types of control charts exist. All are similar in structure, but the specific formulas used to compute control charts are different. Moreover, different types of charts are used for different types of metrics. A continuous metric is one that's calculated from data that are measured as a degree of conformance to a specification on some continuous scale of measurement. Examples include length, weight, and time. Continuous data usually require X bar charts and R charts. A discrete metric is one that's calculated from the data that are counted. Here we can count the percentage or the number of parts within tolerance, the percentage or number of orders complete, and the percentage or number of complaints. These are examples of specific metrics and usually require control charts that we call P or C charts. To determine if a control chart is in control, we generally look at 4 indicators. First, we don't want any points outside the control limits. Second, approximately an equal number of points fall above the line and below the center line. Third, points fall randomly above or below the center line. And fourth, most points are near the center line, and some may be close to control limits. Here's a sample of an in-control R or range chart. See how there's a lot of distance to the control limits? The data is pretty random, and there's no apparent upward or downward trend. Now, when it comes to looking for whether or not a process is out of control, we also look at 4 indicators. First, any points, even 1, fall outside the control limits. Students often say that 1 point isn't enough for a process to be out of control. Even if 1 of 100 falls outside the limits, the process is not in control. Second, there may be a shift in average value. Third, there may be a gradual trend towards the upper or lower bounds that could indicate that while the process is in control now, it could fall out of control if the trend continues. Fourth, there may be a cyclical pattern suggesting a repeating condition. For example, if lattes are too cold during the same 4-hour period every day, this could be the result of an inadequately trained barista, and the out-of-control conditions are occurring only during his shift. Here's an example of an out-of-control X or mean chart or average chart. See here how 1 point falls out of the lower control limit, and see how 2 more were pretty close to falling out as well. Finally, notice that there appears to be a trend towards the upward control limit, and the process may fall out of control again if the trend continues. SPC seems easy enough, but there are some practical issues involved in effectively implementing it. The first is sample size. A small sample size is desirable to keep the costs associated with sampling low, but on the other hand, large sample sizes provide a greater degree of statistical accuracy in determining the true state of control. Large samples also allow smaller changes in process characteristics to be detected with higher probability. Next, managers must also consider the sampling frequency. Taking large samples on a frequent basis is desirable but not economical. There's no hard and fast rule for the frequency of sampling. They should be close enough to provide an opportunity to detect changes in the process characteristics as soon as possible and reduce the chances of producing a large amount of non-conforming output. Finally, SPC is a useful methodology for processes that operate at a low sigma level, for example at a 3 sigma level or less. However, when the defect rate is extremely low, standard control charts aren't effective. Ultimately, processes are designed to hopefully produce a consistent output that meets design specifications. If we can get that, then we have what we can call a capable process. Process capability refers to the natural variation in a process that results from common causes. A process capability study is a carefully planned study designed to yield specific information about the performance of a process under specified operating conditions. Generally, process capability is based on 3 sigma quality level, where, in a normal distribution, 99.73% of the observations will fall within plus or minus 3 standard deviations from the mean. Thus, a process that is in control can be expected to produce a very large percentage of output between plus or minus 3 standard deviations of the process average. 2 common measures of process capability are the process capability ratio, CP, and the process capability index, or CPK. The process capability ratio, or CP, is calculated as the difference between the upper and lower specification limits divided by 6 standard deviations. This is the range between minus 3 and plus 3 standard deviations on either side of the average. This is not meant to suggest that this is a 6 sigma quality program. The process capability index, or CPK, looks to see if a process tends to favor one side of the design specifications over the other. and so we determine the CP of both the upper and lower sides. The CP for the upper index is simply the upper specification limit minus the average, then divided by 3 standard deviations, or 3 sigma. And the CP for the lower specification is the average minus the lower specification limit divided by 3 sigma, or 3 standard deviations. The CPK then is the lower of these two calculations. Let's look at an example of process capability. Let's say we want to develop a capable process for steaming milk consistently for the perfect latte at Starbucks. Now let's say we have an automatic steaming machine that's designed to steam milk to between 155 and 165 degrees Fahrenheit with an average temperature of 160 degrees. Now let's say that after gathering the data, our process is actually steaming milk to between 150 and 170 degrees, still with an average of 160. In this case, the CP would be less than 1 because the output falls out of the design specifications and the process is not capable. This process or machine is steaming milk that's either too cool or too hot versus the design specifications. Let's look at a slightly different situation. Again, say our design specification is to steam milk to between 155 and 165 degrees Fahrenheit with an average of 160. Now, based on the data, our process is doing just that. In this case, the CP and CPK would both equal 1 because the range of output and the average meet the design specifications exactly. We would say this is a capable process. Let's try a third situation. The design specs are as before, but now the observed range of output is between 157 and 163 degrees, still with an average of 160. In this case, the CP would be greater than 1 because the range of output is better than the design spec. We can say that this process is very capable or more than capable. Finally, one last situation. The design specs are the same, but now the data shows the process is steaming milk to between 157 and 167 degrees Fahrenheit with an average of 162 degrees. In this case, the CP can equal 1 because the range is still 10 degrees, but the CPK is less than 1 because the process is no longer centered and the output falls outside of the design specifications, and the process actually favors the upper specification, meaning that it's steaming milk to temperatures slightly hotter than the design specifications. Quality control is vital in ensuring consistent service experiences and creating customer satisfaction. The consequences of a lack of effective quality control systems and procedures can be serious and potentially cause large financial losses or affect a company's reputation. This is why many companies use statistical process control to ensure a consistent and repeatable process to produce consistent output by measuring and monitoring output to desired standards and specifications, and identifying out-of-control conditions created by assignable cause variation so management can take corrective action to prevent the condition from happening again.